Oh, hi Denisha.
Hey, hi Charlie.
Denisha,
Yes.
here I have something.
Wow.
Have you ever thought that this can only have one color?
What if I told you there's a scientific technique that can uncover the hidden colors inside your favorite fruits?
Oh wow!
Let's hear this explanation.
Wondered how scientists can tell what ingredients are hidden inside something that looks completely mixed together. It sounds a bit like a detective work, doesn't it? Well, today we're going to explore one of the simplest yet most fascinating techniques used to solve that mystery, and that is paper chromatography. So, you may ask, what is exactly chromatography? Chromatography is a laboratory technique used to separate the different components of a mixture. The word chromatography comes from the Greek words chroma, meaning color, and graphy, meaning to write. Although it was first developed to separate colored substances, chromatography is now used to separate and analyze many different types of compounds, whether they're colorful or completely colorless. The basic idea is actually quite simple. Imagine you're in a shopping mall during a huge sale. Everyone starts at the same entrance, but not everyone walks at the same speed. Some people stop at every shop, while others head straight to their favorite store. In chromatography, the substances in a mixture behave in a similar way. Some move faster while others move more slowly, causing them to separate from one another. There are several types of chromatography, each designed for different purposes. Ones include paper chromatography, which uses special paper to separate substances. Thin layer chromatography, or TLC, which uses a thin layer of absorbent material on a plate. Column chromatography, often used to purify chemicals. Gas chromatography, which separates gases and volatile compounds. And lastly, high-performance liquid chromatography, or HPLC, a highly accurate technique widely used in research, medicine, and industry. In today's experiment, we'll be focusing on paper chromatography because it's simple, affordable, and a excellent way to understand the basic principles of separation. But paper chromatography isn't just something you do in a university laboratory. It has many important applications in the food industry. Scientists use it to identify food colorings in sweets, soft drinks, sauces, and other processed foods. It also helps detect artificial dyes, check the purity of food ingredients, and monitor product quality. Food products meet safety standards before they reach consumers. So, the next time you enjoy a brightly colored candy, a colorful drink, or even a trendy rainbow dessert, remember that scientists have techniques like paper chromatography to make sure those colors are safe and meet quality standards.
Paper chromatography is an inexpensive analytical technique used in chemistry to separate or identify dissolved chemicals such as food dyes or inks. Paper chromatography separates a mixture's components by distributing them between a stationary phase and a mobile phase. As the mobile phase travels up the paper via capillary action, it carries the components of the mixture. Separation occurs because different components in the mixture have varying affinities for the stationary phase versus the mobile phase. Components that interact more strongly with the water on the cellulose paper travel slower and lag behind, while components that prefer the moving solvent travel faster and move further up the paper. In paper chromatography, the mobile phase is the solvent or mixture of solvent that moves through the paper by capillary action. Do you guys know what does mobile phase do? Let me explain. Mobile phase carries sample components along the paper. Different substances dissolve in a mobile phase to different extents. Substances that are more soluble in the mobile phase travel further up the paper. Substances that are more strongly attracted to the paper move more slower. For example, if a mixture in dyes is placed on chromatography paper and the bottom of the paper is dipped into water, The water acts as the mobile phase, while the paper cellulose acts as the stationary phase. As water rises, it carries the dyes at different speeds and eventually separating them. Factors that influence the result for paper chromatography. First, the type of solvent or mobile phase used is very important. Different solvents have different abilities to dissolve substance. A suitable solvent will produce better separation of the components. Second, the nature of the sample may affect the results. Components that have different solubility and polarities will separate more easily, while similar components may be difficult to separate. Third, the type and quality of chromatography paper can influence the movement of substance. Different paper have different adsorption properties, which affect the rate of migration. Fourth, the amount of sample applied should be controlled. Applying too much sample can produce large and blurry spots, making the results difficult to interpret. Fifth, temperature and humidity can affect the movement of the solvent and the interaction between the sample and the paper. Changes in environmental conditions may lead to variance in the results. Finally, the development time is important. If the experiment stops too early, the components may not separate it completely. If it runs for too long, the spots may become spread out and less distinct.
Now, let's look at the methodology. Firstly, preparing the stationary phase. Cut a sheet of chromatography paper made from cellulose to fit inside the developing chamber. Using a pencil, draw a straight line about 2 cm from the bottom edge as the origin line. Secondly, spotting the samples. Using a clean capillary tube, apply a tiny drop of food dye sample onto its respective mark on the origin line. Keep the spot small, about 2 to 3 mm in diameter, to prevent smearing. Allow the spots to dry completely. Thirdly, developing the chromatogram. Pour the mobile phase solvent made from a mixture of isopropyl alcohol plus water and ammonium hydroxide into the developing chamber to a depth about 1 cm. The solvent level must be below the pencil origin line so it doesn't dissolve the spots directly. Cover the chamber and let it sit for 20 minutes to allow the air inside to become saturated with solvent vapor. Then, carefully suspend the paper vertically inside the chamber, dipping the bottom edge into the solvent. Seal the chamber lid and let the solvent ascend by capillary action until it reaches about 2 cm from the top edge. Finally, drying and marking. Remove the paper from the chamber, then immediately use a pencil to lightly trace the highest point reached by the solvent liquid. This will act as the solvent front. After that, allow the paper to dry completely. Now, let's move to RF value quantification. To identify components, we need to calculate retention factor for each distinct spot using the following formula. For example, here we have sample A with the distance of 7.3 cm. So, to calculate the value for reference A, the sample A distance 7.3 cm must be divided with 9.2 cm, which is the solvent front distance. And then we get 0.79 as the answer for the RF value for sample A.
And just a wrap on paper chromatography. Although it may look like a simple experiment, it's actually a powerful technique that helps scientists to separate, identify, and analyze the different substances hidden inside the mixture. By watching how each component travels across the paper and calculating its RF value, we can compare and even identify unknown compounds. What's even cooler is that paper chromatography isn't just used in school labs. It's widely used in the food industry to check the food colorings, detect contaminants, and make sure the food that we eat is safe and meet quality standards. See colorful candies, drinks, or snacks? Remember that a simple strip of paper can reveal what's really inside. We hope this video has helped you understand how paper chromatography works and why it's such an important tool in science. Thanks for watching and see you in the next experiment.